Here's a closer look at the simplest possible diatomic molecule. The simplest possible molecule is the hydrogen molecule ion. It's H2+. So you have two nuclei. Let's call that nucleus A and nucleus B, separated by a distance r. Okay? And there's only one electron. So a molecule must have at least two nuclei, right? And the simplest molecule is one that has only one electron. So it's actually a molecule ion, H2+. And so this is a fairly simple problem that you can solve the electronic Schrodinger equation. So if you solve the Schrodinger equation, the electronic Schrodinger equation, these are the potential energy curves that you'll generate. Okay? So the lowest electronic state is called the 1 sigma, or the first sigma state. The first excited state is called the 2 sigma. Similar to 1s, 2s, right? And the scale I have on this diagram right here, the energy unit is in Hartrees. 1 Hartree is 27.2 electron volts. So let's take a look at this. The distance right here is in Bohr. So what is the equilibrium internuclear distance between the two in the lowest electronic state? You get about two Bohrs. Okay. And look at what's the dissociation energy for this? This is negative. It approach. Okay. Dissociation energy is how much? It's 0.6, 0.5, so that's about 1/10 of a Hartree. Okay. Now, one thing you'll notice is that the potential energy approaches negative 0.5, negative 0.5 actually, as R approaches infinity. What's negative 0.5? What's negative 0.5 Hartree? What's a Hartree again? 27.2 electron volts, right? So negative 13.6 electron volts. So relative to 0, this is negative 13.6 electron volts. Why do you think that approaches that limit? What happens when the two nuclei separate? You have H2+. When they separate, one is a hydrogen atom, the other is H+. So this negative 13.6, that's just the ground state of a hydrogen atom. So that's the energy of the 1s electron, 1s orbital in a hydrogen atom. Okay? So like I said, each of these potential energy curves represents an electronic state of hydrogen. Okay? Each point on these curves represents a wave function and an energy. Okay? So each of these electronic states is a function of just the coordinates of one electron, right? We only have one electron. And so we refer to these as molecular orbitals. Just like a one electron function for atoms would be an atomic orbital, in molecules with one electron, the wave functions are also known as molecular orbitals. Names of H2+ molecular orbitals, very similar to atomic orbital names, except we're using Greek letters. Instead of SPDF, we use sigma, pi, delta, phi, SPDF, as codes for the quantum number lambda, which is 0, 1, or 2. And what did we... in the case of atoms, we said though S, P, D, and F were codes for the quantum number L, right? 0, 1, 2, 3. Greek letter for L is lambda. In the case of diatomic molecules, in the case of H2+, lambda is just the absolute value of the M quantum number. And M is the quantum number for the Z component of the orbital angular momentum. Where your z-axis, if this is your two atoms, let's say this is A and B, okay, your z-axis is the internuclear axis. It's the line that joins the two nuclei. Okay, so that's your z-axis. So for pi states, what's your L sub z? So what would be L sub z of a pi state? It's going to be lambda h bar. Instead of m sub L h bar, it's going to be lambda h bar, right? So plus or minus lambda h bar, actually. It's m h bar, okay? And so pi states we say are doubly degenerate. There's two ways you can have a pi state. There's two ways that it's the z component of its orbital angular momentum can be oriented. Okay, plus h bar or negative h bar. So non-sigma states, the pi state, the delta state, the phi states, those are all doubly degenerate states. Okay, so this would be plus or minus h bar. For delta states, what would be your L sub z? Plus or minus 2 h bar. Okay. Now, these numerical prefixes 1, 2, and so on, those are just our way of differentiating between states that have the same lambda, same absolute value of m. So they're just counting numbers, just like you go 1, S2, S3, S. So the first sigma state is called 1 sigma. The second sigma state, you can refer to that as 2 sigma. Now, the name for molecular orbitals generally include labels that describe the symmetry of the electronic wave function. Okay, and the symmetry in the case of a diatomic molecule like H2+ is based on the origin being set at the midpoint between the two nuclei. Okay, and then your internuclear axis is the z-axis. Okay, so this is going to be your xy plane. XY plane. Right. Now, the names might have a G or a U label attached to it. G stands for gerade, and U stands for ungerade. What those simply mean is that the function is gerade if your wave function is symmetric with respect to inversion. What does inversion mean? Let's say you have a function f of x, y, z, right? If you apply the inversion operator on it, or the parity operator, all you have to do is replace x by negative x, replace y by negative y, and replace z by negative z. If by doing that, you still get the same value for the function, then we say your function is gerade. It's symmetric with respect to inversion. If by doing that, you get the negative of the function, then your function we say is antisymmetric, is ungerade. Okay? So if I had the parity operator or the inversion operator operating on a pi state, pi u molecular orbital, what would be my answer here? Is this symmetric or antisymmetric with respect to inversion? So the answer here would be negative pi u, negative of the original function. If I apply it on sigma g, you still get back sigma g. Okay? So names for molecular orbitals generally provide information about the symmetry properties of those orbitals. Now, names of orbitals may also have a star as part of the name. So for example, you can have a pi g star orbital. Okay, so if you have a star label on the name of the orbital, that simply means that your orbital is symmetric. I'm sorry, if there's no star, that means it's symmetric with respect to reflection through the xy plane. If you put a star, it's antisymmetric. Okay, so if here's your nucleus A, nucleus B, where's our z-axis? That's the line, internuclear axis, the line joining the two. Where's our origin? Halfway between nucleus A and nucleus B. This is our, so that's our z-axis. This is our x-axis. Your y-axis is right here. If you're going to reflect through, if you're going to do a reflection through the xy plane, okay, and you end up with a negative of the function, then you put a star in the name of that function. Okay, if it's symmetric, then there is no star. Okay, so in other words, a star means what? The xy plane is a node, right? Your function changes sign from positive to negative or negative to positive. So if your xy plane is a node, you're looking at a region, a plane between the two nuclei where there's low electron density. Okay? And when that happens, generally what that tells you, that's an unstable situation. We have two nuclei, you know, with no electrons, minimal electrons between them. So that's what we would call an anti-bonding case. That would generally be higher in energy, lead to higher energy. Okay? So the reflection operator, like I said, just replaces Z by negative Z. You just go across the XY plane. And so if there is a star in the name, you're dealing with a wave function that is anti-symmetric with respect to reflection. The reflection operator is usually represented in this case by sigma H. H means the horizontal plane. That's the plane that is perpendicular to the Z-axis. Okay, so we take the Z-axis as the vertical, the XY plane is the horizontal plane. So sigma H is reflection through the horizontal plane. And if you apply that operator on your wave function and you get back the negative of the original wave function, then you have to put a star in the name of that function. Okay? So you have an anti-bonding orbital. So in this particular case, if I have sigma H operating on the pi G star, what would I get? Is this going to be symmetric or anti-symmetric? Anti-symmetric, so I'm going to get negative pi G star. You have an anti-bonding orbital. Okay? And why is psi electronic with a star called anti-bonding? Because you're dealing with a situation where there's a low electron density between the two nuclei. So what do you know about two nuclei? Two positive charges. They repel each other. Right? So that's an unstable situation. Right, so these are the lowest electronic states for the H2+ ion. Okay, you'll notice the first sigma, okay, it's down here. You'll notice it has a deep well, you might say. So you have what's called bound states here, right? And so at intermediate distances, it's possible for the two hydrogen nuclei to be bound to each other. Basically, what are we saying here? Let's say you have your separation at this distance right here for, let's say, four atomic units, 4 Bohrs, okay? So they're going to approach each other, and then what happens? Speed up, and then once they pass this distance, slow down, and then eventually when they get to this distance, they stop. And then they separate again. They move far away, speed up, slow down, stop, speed up. Okay? So speed up, slow down, stop, and then turn around and back and forth, back and forth. Okay? So no. I'm sorry. Add to the right. Let me see if I can blow this up. I can zoom on this. Where's the zoom function? Okay, let me see if I can make it finer. All right. So from, let's call this point B to point A. Okay. So B and A would be what you would call your classical turning points, right? Distance B is as far as they can be from each other. Distance A is as close as they can be to each other if their total energy is only this much. Okay? If the total energy is lower, what happens? They can only go from, let's call this point C to point D. They can only be as far away from each other as point C, as distance C, and as close to each other as distance D. in other words, the higher the energy, what happens? At low energy, they'd be oscillating between these two distances, right? At a higher energy, they can oscillate further away from each other. And at even higher energies, even further. If you give them enough energy, they will just separate and not come back. Okay? So that's why we say this is the minimum, this minimum energy here between this limit at R infinity and at the minimum, that's your dissociation energy. That's the minimum energy, that's the minimum relative energy that the two nuclei need to have in order to be able to separate from each other. So anything, any energy level that's down here, okay, any energy level that's below this one, you have what's called a bound state. So energy less than 0 would be bound state. Okay, if we take this as R0, this is not 0 here actually, so this is going to be less than 0.5, negative 0.5. On this scale, your limit is negative 0.5. So at energy less than negative 0.5, you have a bound state. Okay? Look at the second sigma state. What do you notice about that? There is no well. Okay? In other words, let's say they have that much energy. Well, they're going to, let's say they're approaching each other. They're going to move that way, right? The distance between them is going to move that way. You're going to get closer. It's going to slow down, slow down, slow down, stop. And what happens? They're just going to speed up, speed up, speed up, speed up, and then reach constant speed, separate from each other, never to see each other again. So this, when you have this kind of a curve, potential energy curve that doesn't have a well, you have what's called a completely repulsive curve. Okay, so this is completely repulsive. So 2 sigma is what you call an anti-bonding electronic state. You're not likely to get the molecule to get stuck together. Whereas this is a bonding electronic state. The molecule, if it doesn't have enough energy, the 2 atoms will get stuck to each other. You form a bond. Okay? So that is how you would interpret those these diagrams. Okay. Now this should be E greater than not 0 but 0.5, since this is negative 0.5. 0 is up here. Okay. So we're comparing it relative to the case where the atoms are free to move from each other, infinitely separated.